derivative. Austin, if you want to move, if that's going to be awkward for you.
I'm good.
Okay. What can we do with the derivative? Okay, we can find slopes. What else did we do with it?
Curve sketching.
Curve sketching, good. What else did we do with it?
Related rates.
Related rates, optimization. Okay, what else? Leaving out one very important thing. PVA. Okay, leaving out PVA. All those were applications of the derivative. And when you got an application of the derivative, what did we say to do on the AP exam? If all else failed, what do you do? Take a derivative and set equals 0. Okay? Now, so our whole first semester was nothing but derivative. Okay? I gave you a position. Remember PVA? That standard function, that is your position. And what did you do? You took the derivative, set equal to 0. You knew what? When your derivative was equal to 0. Okay? Derivative is equal to 0. Okay, what did that tell you, PVA? When your velocity was 0, which meant what?
Was at rest.
It was at rest. It was at rest. Okay? So, I gave you position, you can tell me all sorts of things, okay? Everybody stand up. Okay, take 3 steps forward. Be careful. Take 3 steps forward. Okay, now this is where you were on December the 15th. Now take 3 steps backwards. Okay, that's where you're going to be on graduation day.
What does that mean?
Okay, what does that mean? Back where you started. Because what you're going to do, second semester, is based on integration. Have a seat. And integration is I start you with velocity. I tell you a car is going 55 miles per hour. And amazingly, you can tell me its position. Now, there was a neat example of this in a book. You've been kidnapped. Okay? You're in the trunk of a car. And it's got a little teeny tiny hole that you can see out of. And you are just conceptually so smart, you can estimate what speed that car's going. So what you do is you got an illuminated watch that you can see in the dark. And you keep checking the watch, and at these intervals you can come up with a speed. So what do you have? You've got a T, and you got a slope, and you realize you have a cell phone in your pocket. And you pull it out and you call the police and tell them exactly where you are at any given time. Because you know the time and you know the slope. So if you're calculus, you can get out of all sorts of kidnapping situations. I know. But the point is, we're going backwards now. We're going backwards. And the first thing we've got to do is we've got to be able to take something called the integral. Now, we've been taking quantities and coming up with a rate of change. Basically, now we're given the rate of change and we're going backwards and coming up with quantities. And the neat thing is, if you're really smart and can figure out how much that car is accelerating, you're going to be able to go back from acceleration back to velocity back to position. But more important than that, okay, visualize a puppy. Cute puppy. Okay, I want a puppy so bad, but I can't have one until cat goes to heaven. Okay, we're outside. We're not talking about my cat. Okay, but visualize a puppy. Okay, what do you know about puppies? They chew, they poop. Okay, they tear things up, right? Okay, so you visualize a puppy makes it to the bathroom. Okay, and here's the end of the toilet paper roll, just absolutely tempting that puppy. Now, what is that puppy going to do?
Pull it down.
Okay, and what's the puppy going to do? He's going to roll, and it's going to end up all over the house, right? Okay, what an integral can do for you is more important even than this going backwards. It's something called accumulation. It's something called accumulation. If that puppy can roll 12 squares of toilet paper per 5 minutes off that toilet paper, how much squares of toilet paper will the puppy be able to roll off in an hour? Okay, that's accumulation. Now, thank you very much. Appreciate it. Now, that's not a really good real life example, okay? But say you are BP Oil Company and you got an oil rig. And that oil rig is just blown up and 11 men have just died. And all of a sudden all this oil is going into the ocean. When the news reports it, they're going to say 100 gallons of oil are spilling into the ocean per hour. Now, where did they get that number, and how do you think they figured it out?
Accumulation.
Accumulation. See, now you're starting to answer right now. Okay? It's accumulation. The integral, the biggest power of the integral is it will answer questions like that. Not the puppy questions. Puppy questions is cute. But they can answer questions like that. They can accumulate things over a period of time. Now, the type of integration we're going to talk about today is the indefinite integral. Now, indefinite integral is not good for much. The indefinite integral is not good for much. Why do we have to learn the indefinite integral? Because we've got to learn the rules of integration. Now, do you remember the rules of derivation?
The rules.
Yeah. Power rule, quotient rule.
Oh, God.
Okay, oh gosh, we got to get all of back in our head again, don't we? It's too cold for the red ball activity. Okay? But now we got to be able to do all that backwards. But the problem is, they don't all just work like back and forth. Some of them are a little bit weird. There is no such thing as a product rule in integration. So we got to learn some new rules. And what we do is we practice these rules on the indefinite integral. The indefinite integral, to my knowledge, has no practical application. It is just like Nathan.
Yes.
You're so
Wait, are
easy
you
to
saying
pick
I
on.
have no practical application?
Okay. Yeah, I did. You made fun of that. Okay, now, would you please sing the ABC song for me?
A, B, C, D, E, F, G, H, I, J, K, L, M, N, P, Q, R, S, T, U, V, W, X, Y, and Z.
Okay, now you've learned your ABCs. Okay, now,
And we got it on camera.
okay, yeah. Now, think about it. The practical application of that song is zero. But if you don't learn your alphabet, what happens?
You can't make words.
You can't read, you can't make words, and you are going to be a bum for the rest of your life. Okay, because people who cannot read have difficulty succeeding in life. Okay, and I don't want to be, mean there. There are people who can't read that are valuable members of society. But in general, the rule is you need to learn to read to be a productive member of society. Okay, you need to learn these rules to be able to move to the application. And that's why we're going to learn the indefinite integral. Now, if I gave you this, what would you tell me?
X squared.
X squared.
times
You're
X.
reading it like it is. What else could you tell me?
X times X.
Okay, good. Now get out of Algebra 1. What can you do with X squared?
Put a number in for X.
Okay, you're still in the stuck in Algebra 1. Okay, take the derivative. What did I tell you? If somebody asks you a question and you don't know what to do, take the derivative and set equals 0. Okay, what's the derivative of that? 2x. Okay, now we're going backwards. This is the derivative. I want the antiderivative. Now, that's actually what you call it. That's what you call it. That's the antiderivative. I want the antiderivative. Okay, well, what's the antiderivative for x squared?
1/3 x cubed.
Shazam. Okay, it is 1/3 x cubed. Okay, it is 1/3 x cubed. Now, it's easy to check him. What's 3 times 1/3? 1. And then drop this. 3 take away 1 is 2. Is that the same answer? Is the derivative of that, that? Yes. So, this is the derivative. Okay? This is the antiderivative. So, y prime is equal to x squared, or you can say f prime of x is equal to x squared. Okay, so we need some notation for antiderivative. We need some notation for antiderivative. And what they do, and I have to be careful how I write this, is you use a capital F. Okay? You use a capital F. So the antiderivative of that is 1/3 x cubed. Now, if your capital F looks like a little f, we're used to that being the original function. Like when we used our f of x notation here, I would have labeled this little f of x because it's the original. I would have labeled it, bless you, little f of x. Okay? But the capital F of x says that I've taken the antiderivative of something. Now, we've got a little bit of issue here. Okay? Would you please take the derivative of 1/3 x cubed plus 4 for me? Take the derivative of that. What's the derivative of that? X squared. Okay, take the derivative of 1/3 x cubed minus e. What's the derivative of that?
X squared.
X squared. Now, how many times could I keep doing that? A gazillion. Okay, so we got a little issue here. How many antiderivatives does x squared have?
Oh dear.
Oh dear, how many?
Infinite.
An infinite number of them. Well, now that's kind of, how useful can this be if there was an infinite number of answers type thing? And that is the problem with the indefinite integral, and I bet you that's why they called it indefinite. Because do we have a definite answer? No. Now, do we have a good idea of something? Yeah, that x squared is probably your most important part. But on every one of these, on your antiderivative, there was some constant out here to get me the same antiderivative. There was some constant out there. So what we say when we did this one, and when, I think Austin's the one that came up with this. Austin's the one that came up with this. Okay, to cover our derrieres, because we could have had a constant there, we don't know if there was or not, we simply put a plus c. We simply put a plus c. When we take the antiderivative, our answer should include a plus c. Now, we're going to have to get used to that, because I'm telling you right now that on quizzes, on tests, somebody's going to forget the plus c. And we get to the point where everybody gets one and they put plus c at the top of the page before they even start working it. So they will remember to put that plus c. Because when you take an antiderivative, you want to put that plus c. Now, I will get tired as a teacher of writing find the antiderivative. And that's where the integral comes in. Now, what does that mean to you mathematically? Summation. And didn't I say that one of the most important things for the integral is accumulation? And when you're adding up those toilet paper squares that puppy's pulling, or when you're adding up the amount of oil that oil drill is filling, aren't you accumulating, aren't you adding up how many gallons of oil and how many squares of toilet paper? So what they did, the guys who came up with the notation, Leibniz, Newton, all of them, and Leibniz is really the one who came up with the integral notation, they realized that the power of this integral was in this sum. So they started out with that, okay? But then it ended up looking like that. Now, how in the world do you go from this to this? Well, that means summation. Doesn't that look a little bit like an S? Okay? Yes. But I bet you they just quickly started doing this and said, you know, we don't have to put a lot of effort into this, and there you end up with your integral sign. So if you see the integral of x squared, that's almost complete in asking you to find the antiderivative of x squared. But what you will always see is you will see a dx out here if your variable is x. And now you have what your problems are going to look like. If I leave this off, I haven't written it correctly. If I leave that off, I haven't written it correctly. And what that is saying is find the antiderivative of x squared, and we already determined the answer to this is 1/3 x cubed plus c. Because we know now that there are an infinite number of answers. Now the question is, if I give you something, you know, Austin just came up with this in his head. Well, now, you don't want so I've come up with stuff in your head when it gets more complicated. You want a rule. Now, what have I given you? I've given you the derivative. I want the antiderivative. So I'm either asking for y, or I'm asking for the original f of x, which the notation is capital F of x. But as we get more sophisticated, it really looks like this. But I'm just giving you the derivative, and I'm asking you for the antiderivative. That's what the integral does. Now, can anybody take what Austin did over here? This is the first rule. This polynomial was the first rule we learned for derivative. Now that's the first rule we learned for integration. I want you to see if you can tell me what you think the rule is. I'd start by looking at what Austin did. Anybody want to volunteer?
Matter cannot be created or destroyed.
Isn't this kind of the same thing? Now, yeah, I agree with that, and I don't know, was that one of Newton's laws of something or another? But have you ever thought about when they
It's
send...
one of the laws of thermodynamics.
But now think about it. When they send rockets off the planet, how come that doesn't change something? Because there's not much weight on the world. And if the population is so much more than it was back in Adam and Eve.
Why has the earth not caved
How
in?
much, how much do we weigh now, all the people on the earth? Okay, but that ain't what we're talking about. What you think? Anybody formulate a rule? Valerie. Go, girl.
You add 1 to the exponent and then multiply the front number by the reciprocal.
Three Shazam. She has just said it beautifully. Now, I'm going to say it a little bit different, but she's absolutely right. But when we take the derivative of something, what is the power rule for derivative? Take the exponent, multiply it, and then subtract 1. So the power rule for derivative, we multiply and subtract. So wouldn't it make a difference? Seem to make sense. What's the difference of multiplying? Dividing. And what's the difference of subtracting? Adding. We're going to do exactly the opposite of what we did. Now, let's look at this first term here. Let's look at the first term. Instead of subtracting, we're going to add. So it's going to be x to the 5th. So we just add 1 here. Okay? And then, instead of multiplying, we're going to divide. So now we're going to divide by that 5. And think about it, when you took the derivative, you multiplied first and then subtract. We're going to do it in the opposite order. So we're not going to multiply and then subtract. We're going to add and then divide. We're even going to switch the order of our operations and switch our operations because we're doing the opposite. On this second one, you add 1 to the exponent. You add 1 to the exponent. And then you divide by that. Now, Allie says multiply by the reciprocal. Isn't that the same thing as divide? Yes. I mean, same idea. I just wanted to use the divide word because it's the opposite of the multiply, which we do when we're taking the derivative. Okay, now here, there's an understood 1. So you add 1, and then you divide by it. understood here?
0.
X to the 0. That's understood. X to the 0 is 1. So now we've got -6. We add 1, x to the 1 over 1. Whatever your exponent ends after you add 1 to it, that's what you divide by. And then you've always got to remember that elusive plus c. There could have been a constant there. We don't know. A constant would have dropped to the 0 out here. And it can be any constant in the world, and we don't know what it is. Okay? Now, I want you to know this is a miracle. I made that up, and for all of these to divide evenly, there was some kind of Freudian slip going on there, because mine never turned out this good. Okay, so your original function becomes x to the 5th minus x cubed plus x squared minus 6 plus c.
Isn't it 6x?
I can't hear you, Katie.
Isn't it 13?
Shazam, it is a 6x. Now, what do you think we're going to call that? Gotta have a name. They've all got a name. What did we call it when we took the derivative? What was that called? NaX to the n minus 1? What's that called? Power rule. That was the power rule. Okay? Now, what do you think we call it for integration? Power rule. Okay? This is the power rule for integration. Okay? This is the power rule for integration. And the power rule for integration if I ask you to integrate ax to the n dx, it will be ax to the n plus 1 divided by n plus 1 plus c. Does that make sense? Now, there is a constant rule for integration. If you integrate a constant, let's see, integral of 5. Integral of 5.
5x.
Let's see. Yeah, we got to get the plus c on there. Okay? If I give you a derivative of 5, then the original function was 5x plus possibly some constant. Constant could be 0. But if I give you, that's called the constant rule, but I really don't think that's even worth listening much. Because really you're doing the same thing. If you've got a constant, you're really using that power rule for integration. You're just realizing there's an x to the 0 at the end, and you're using that. Now, there is another one that is even more important than its counterpart on the derivative, okay? And that is the constant multiple rule. And this was not real important when we did derivatives, but it is going to be very, very important when we do integration. If I've got k x dx, and that k stands for a constant. And that k stands for a constant. And the reason they don't put c in there for a constant is they don't want you to get confused with the c at the end. This is equal to k on the integration of x dx. It's almost like that integral sign is a semi-permeable membrane. Doesn't that make me sound smart, like I know science? Okay? It is almost like a semi-permeable membrane. Now, what does semi-permeable membrane mean in science? What? Some things will go across it and some things won't. That's what a semi-permeable membrane is. It usually has to do with the size of what it's trying to get through. Well, this is semi-permeable in that you can take a constant out. Constant can get through. variable can't. You can move a constant on the other side of the integral sign, go ahead and integrate, and then distribute the constant. Now, let me give you an example. Now, I'm going to show you in a minute why that dx is necessary. But let's just keep putting it there because it's the right thing to do right now. Now, if I ask you to integrate that, now I want everybody to integrate it just using the power rule for integration. Everybody please integrate it. Everybody please integrate it. Just using the power rule for integration. Don't do anything else. Just your power rule for integration. Philip, tell me what you got when you got it.
One half x to the 10th plus 3x to the 5th minus 5x squared.
What's your magic last
Plus
name?
C.
Yep. Okay. What happened to what?
To the dx.
Okay. You antiderivated a derivative, so they canceled each other out. This and this canceled each other out. This means take the derivative. This means take the antiderivative. They cancel each other out. And here again in a minute I'm going to show you why that dx is important. Because it looks like it's unnecessary. Okay, now, that is correct. Now I was going to brag I can do this in the head like that, but then I wrote 5/9 because I forgot when I added 1 to that to put a 10 there instead of a 9. You are going to be able to do this as fast in your head as you can the derivative once we practice it. Once we practice it. Now, here's my problem. We've been doing derivative for a semester. I'm going to get up here, I'm going to be working a problem, I'm going to be doing that, and I'm just going to take the most gorgeous derivative in the world, and what am I supposed to be taking? The antiderivative. So, all of a sudden now, the question was first semester, if you don't know what to do, take the derivative and set equals 0. Well, we got an issue now, because now the second derivative is all about integration. And are we going to have to know when to take a derivative and set it equal to 0 and when to take the antiderivative? Yes, and we'll learn to do that. But I find sometimes I'm supposed to be taking the antiderivative and I'm taking the derivative because my brain is just locked on derivative. Now, you got your answer to it. Now, I want to use the constant multiple rule. What constant do you think can be factored out of there? 5. Okay. Now, you don't, taking the x's out, you don't want to do that because I've just said it's semi-permeable. The x's won't go across the integral sign. But I'm going to take, and I'm going to factor out a 5, and that gives me x to the 9th plus 3x to the 4th minus 2x dx. And all I did was factor out that 5. Now, I would never do that on a problem like this. I would do just exactly what we did. I'm just proving to you that that works because there's some problems you have to do this. We're going to get into some things I call yellow submarines. And we're going to have to start doing some adjusting. And the yellow submarine is the opposite of the chain rule. There is no chain rule for integration. There is no product rule for integration. And sometimes you're going to have to be able to do this. Now I'm going to pull the 5 outside the integral sign. And I'm just going to integrate x to the 9th plus 3x to the 4th minus 2x dx. Okay, so Now, let's integrate that. X to the 9th is 1/10 x to the 10th plus 3/5. Wait a minute. Did I do the right one? I'm doing this one right here. Well, yeah, x to the 10th plus 3/5 x to the 5th minus 2/2 x squared plus c dx. Now, did I do that right? You're integrating this. X to the 9th is 1/10 x to the 10th. 3x to the 4th is 3x x to the 5th. Minus 2x to the 1 will be minus 2 over 2x squared plus c. Well, that goes away. Nothing else will clean up. Okay, now this 5 was on the outside. You redistribute it, and you get 5/10 x to the 10th plus 3x to the 5th minus 5x squared plus c. Now, is this the same thing as the black? Yes. Now, I repeat, I would never have pulled that out to work this problem. But you need to know this rule is an important rule for something we're going to be doing later. Yes.
So when you do this, you don't distribute the 5 to the c?
Okay, now, here's a good question. Now, c is a constant, right? What's 5 times a constant? Is 5 times a constant a variable? 5 times a constant is a constant. Okay, so we just leave it plus 3. Now, if you wrote 5C on your paper, you'd probably get a frowny face because it's just not done. But since 5 times a constant is still a constant, we don't write it. Okay? Okay, now. Now look at that real quick, and what word does that look like? Don't say it, we're big video here. Okay? Okay? What does that word look like?
E to the A.
Okay? Now, this is the way that, I saw this at a AP workshop one time. This is the way to help you remember you have to do dx. That is the only thing, when you write it like this, that's what you do in your bedroom after you're married. Okay? Okay? That is not calculus. That is not calculus. Okay? Okay, this is calculus. Now, that is just a silly way to help you remember that. First of all, answer the question, what is the integral of e to the x to the dx?
E to the x.
E to the x, what?
Plus c.
Okay, the answer to this is e to the x plus c. The answer to that, because e to the x is its own derivative. I like that one, that's my personal favorite. Gotta get the plus c on it. So now, let me show you why this is important. Preliminary reason it's important. If I ask you to integrate this one, everybody integrate that one. Okay, what are you getting?
2x plus c.
What?
2x plus c.
2x plus c, is that what the rest of you got? No,
Oh.
the answer is 2z plus c.
Of course it is. I don't know how I
Yeah.
forgot that.
Okay? See, it's like, that's not fair,
Okay.
because this does not tell you what variable I'm talking about.
Oh.
Now, if I'm talking about gallons of oil, then I'm trying to figure out over the amount of time how many gallons of oil are spilled into the ocean, then this would be a G. But you don't know that unless I put that out there. Now, 99% of the time, is it a dx out there? Yeah, we work in x's. You know, I don't know who came up with that, but we work in x's. Okay, so yes, most of the time it's an x. And the first year I taught calculus, I thought that was the most useless thing in the world. You're always going to find, also going to find out when we start doing this yellow submarine, getting into this idea of the reverse chain rule, that this has a little bit more purpose than just telling you what variable. But for right now, it is, if you're given some kind of constant and you're not given this, you don't know what variable they're talking about. So know that that needs to be there. That it needs to be there, whether or not we feel like it's necessary or not. You know, it's kind of like your, you know, appendix or your tonsils or something. You know, at some point, wasn't there a reason for your appendix? I think it was something to do with people ate dirt and they had to, I don't know. But anyway, okay, that's kind of like this. Sometimes it's going to be useful, but rarely. But it needs to be there.
This is the best class of video.
Okay, I may be thinking about gizzards and the chicken is why they've got, because they eat gravel, but never mind, okay, whatever. See, I look like I'm smart with science and then it backfires on me. Okay, now, what about your trig functions? Can you go backwards on your trig functions?
Why not?
Oh, yes you can, okay. If you have the integral of secant squared x dx, what's the integral of secant squared x dx? Not everybody at once. Don't overwhelm me with answers.
Tangent x plus c.
Secant x tangent.
Tangent x plus c.
Tan x plus c. Okay, what is the derivative of tan x?
Secant squared x.
So what is the antiderivative of secant squared x? Tan x
Tangent
plus c.
x
Are
plus
we
c.
going to have to get these derivatives back in our brain?
Yes, we
Yes.
are.
We're going to have to get these derivatives back in our brain because we're going to have to be able to do these. Look at your worksheet. Look at number 19. Now, you always have available to you what you've learned in algebra and what you've learned in advanced math. Okay? Secant x is not the antiderivative of anything. I mean, secant x is, I said that backwards. Secant x is not the derivative of anything. Secant x plus tan x is not the derivative of anything. But you have one more valuable property of integrals. Does algebra 1 tell me in trig that I can distribute that secant x in that parentheses? So this is the same thing as the integration of secant squared x plus secant x tan x dx. Everybody okay with that? Now, that's cute, but that's not calculus. What is calculus is the laws of integration allow me to separate that into two integrals. So that is the same as the integration of the secant squared x dx plus the integration of secant x tan x dx. Now notice I pulled the dx on both of them. And what I've taken is I've taken one long integration and I've broken it up into two very manageable pieces. Now, what is the antiderivative of secant squared x dx?
Tan x plus
Tan
c.
x plus c. Now get in the habit of that plus c. It's going to save you some heartbreak later. Okay, now over here, what is the antiderivative of secant x tan x?
Secant x plus c.
Okay, secant x plus c.
Plus c.
Now, leave that on your paper like that, and I'm going to hit you with the orange bat.
Oh,
What is a constant plus a constant?
A constant.
A constant. So what is the answer to this problem?
Tan x plus
Tan x plus c.
plus
Plus c.
What's it? So, what's the moral of this story? You can break intervals up, and we will be doing that a lot. If it's addition or subtraction, in other words, you can break up terms. You can break up terms. If it were to be, if it had been like sine x times, integration sine x times cosine x, you cannot split multiplication or division. You can only split terms. You can only split terms. This rule only works if you have got terms. Now, number 11 looks like fun. Let's see if we can squeeze number 11 in here. Now, what did we have to do with derivatives when we were faced with radicals? What did we do with them? If we were asked to find the derivative of something, then we had a radical. Right, we rewrote it. Sometimes you got to rewrite an integral. This is going to be 3u to the negative 1/2 du. Where did the negative come from?
The bottom.
Did we have a ticket to ride situation?
We do.
We did. I wanted it off the bottom, and I wanted it out from under the radical, so that became u to the negative 1/2. Now, do I just use the power rule for integration? Yes. Okay, now what's it going to be? Okay, I'm going to add 1, so that's going to be u to the 1/2. And then I'm going to divide by 1/2 plus c. Now, do you think I'm going to let you leave it like that? Not on life. What's 3 divided by 1/2? 6. And your answer is 6u to the 1/2 plus c. And now, isn't it neat? Because can you quickly check to make sure you're correct now? What's all you got to do? Take the derivative of this, and what should you get? That. So y'all, this is very much tied into what we've been doing. This is not like new, it's just like backwards. Any question about this?
Is that a 6u?
That's a 6.
Yes. Doesn't look like one, but yeah.
Now it's like a 6e.
You. Question. Okay, for homework.
Yeah.
Out of practice for homework. You need a lot of it. I
Still
want you to work 1 through 18. Now, I've already done 11 for you. So that's only 17 total. 1 through 18. We could say 1 through 19, but then I've done 2 for you. But it's still 17 total. Any questions? For those of you out in YouTube land, I'm glad that you could join us today. Can we leave the sex part off of YouTube?
Miss Sutton said sex.
No.
They might take that off YouTube. Take off the sound. There we go. We're now. Yeah, unrecorded.
Won the magnet race last week.
Of course it did.
I mean, last 6 weeks. And I went ahead and took all the magnets down because I wanted to clean slate for your magnets today. But tomorrow when I got the coats and stuff, when everybody's back and we do the Shazam drawing, if I forget to do that because I'll look up the magnets, you're going to have to run. Okay, because you have already coats. I've got 2 backsliders in here. Philip and Austin. Do we always do these on notebook paper? Yes,
I
don't do
guess.
them on the worksheet. Don't I guess me. Okay, I thought I had you trained, and here you are backsliding. Okay, I want that stuff on notebook paper, not on the worksheet. Okay, now here are the correct answers. Would you please check your papers? Number 1 is x cubed plus c. Number, hey, turn that off. I don't want those kids to get the answers.